This V0 to Vi is known as open loop, the closed loop gain of the inverting amplifier. EACL is V0 to Va, that is equal to minus Rf by R1 from this expression. So there is an alternative way to do this again. Let us suppose this node voltage is Va. So apply Kirchhoff's current law. This, what is Kirchhoff's current law says? Algebraic currents at a node equal to 0. So this current plus this current plus this current equal to 0. That is Va. What is this current? Va minus Vin by R1 plus 0 plus Va minus V0 by Rf equal to 0. By doing that also we will get V0 by Va as minus Rf by R1. Okay. So this is about inverting amplifier. Coming to non-inverting amplifier. In non-inverting amplifier we are connecting the voltage to the non-inverting terminal, that is plus terminal, and minus terminal is grounded with this resistor. Okay. So in inverting amplifier we have a resistor connected to negative terminal. Non-inverting amplifier also we have a resistor connected to the negative terminal only, and here also we are connecting a feedback resistor from output to the negative terminal. But the only difference is, instead of giving voltage at this non-inverting inverting terminal, we are connecting the voltage to the non-inverting terminal. Okay, remaining things are same. What will you get? So according to the concept of virtual grounding, I am applying the voltage here. This same voltage appeared at this point also. Okay, what is this current? V in minus 0 by R1. Where I am getting this current? From here, obviously, maybe because there is no current in and out of this point. Where I am getting this current? I should get from here, right? What is this current? V0 minus Vin by Rf, that is equal to Vin minus 0 by R1. By equating these two, we will get the expression for V0 to Va, that is open loop gain of a non-inverting amplifier. Otherwise, here also we can apply nodal analysis, that is Vn minus 0 by R1 plus Vn minus 0 by Rf plus 0, that equal to 0. Using that also we can apply, we can achieve V0 to Vn ratio as 1 plus Rf by R1. Okay, here if you see V0 and Va directions are same. In earlier case, V0 by Va equal to minus Rf by R1, that is V0 equal to negative of Va, but here V0 is positive of Va, 1 plus Rf by R1 times of Va. So there is no inversion. You will just amplify the signal, not by doing any change in sign. Means if we apply input voltage as a sine wave, output also obtained as a sine wave without any phase shift. But in inverting case, we will get a phase shift of 180 degree. Okay. So slew rate of an op-amp. Slew rate means if I am applying an input signal like this, my output will not suddenly raise like this. It will slowly raise like this. It is something like a rate limiter. Means it won't allow suddenly change like this. This is useful while charging batteries, not to allow a sudden input spike as the input to that. Okay, it is something like a rate limiter. We will say it is a rate limiter. Okay, slew rate. A slew rate is a property of an op-amp. What it does inherently, its units are volts per microsecond. It won't allow the output voltage also suddenly like input voltage what we are applying at the input terminals. Okay, its voltage slowly rises like this. Slow in the sense how much slow? In microseconds. We cannot identify without naked eye. We will see hopefully as a output signal as a square wave, but if we expand that one in time scale, then we can see this slope. Okay, if you expand that one in your CRO time scale, then only we can see this. And so this slope is called a slew rate. A typical general purpose device may have a slew rate of 10 volt per microsecond. Okay, this means that when a large step change is placed at the input like this, the output Okay. The electronic device would be able to provide an output of a 10 volt change in 1 microsecond. Okay. So if you take this duration as 1 microsecond, the change is 10 volt. Okay, 10 volt per microsecond. If this is 100 microseconds, then 1 volt change. If it is 1 microsecond, 100 volt change. Okay, something else. So 10 volt per microsecond. In 1 microsecond, this 10 volt. If it is 0.1 microsecond means 100 volt, something like that. Supply voltage rejection ratio. Actually, we have seen 5 terminals for an op-amp. Input 2 terminals and output 1 terminal, and V plus V minus are supply terminals. So if you consider that supply voltage applied to the supply terminals, SVRR is the ratio of change in op-amp's input offset voltage to change in supply voltage. Okay. Input offset voltage means, I already told you, when there were no input, we were getting some output at output pin, that is offset voltage. When there is a change in supply voltage, that is a V plus and V minus signals, V plus and V minus means, if there is a change in the supply voltage applied to the V plus and V minus means, what is the change in the output offset voltage? Okay, means something like see here. So I am not applying any input voltage. If there is so here I am giving plus 5 volt and minus 5 volt. If this is suddenly changed to some 6 volt. Okay, so without any input voltage, without any input, my output is some 50 volt, so 0.5 volt offset voltage. My output voltage is 0.50 volt without any input voltage. If there is a change of plus 5 to plus 6 volt, what is the change in this value? What is the change in offset value? The change in supply voltage. Provided these two are 0, I am not applying any input voltage. This is 0 volt and this is 0 volt. If I am not applying any input voltage, with this small change in supply voltage, what is the change in offset voltage? Without giving input voltage also, we are getting some voltage at output, means this is offset voltage. What is the change in offset voltage to change in input voltage is supply voltage rejection ratio, or PSS, power supply sensitivity. It can be expressed in microvolt per volt. Okay. So delta VIO. So this is delta VIO. Delta VI means delta VI at the output. Okay. Delta VI at the output is delta VIO to change in supply voltage, delta V. So this delta V is this one, 5 volt to 6 volt. 6 minus 5 is this delta V. Delta VIO is this one. Okay. Change in this voltage. Delta VI is this one. Delta VI at the, so offset causing delta VI is delta VIO. Without input, this is the offset voltage. So this voltage is SVRR, 150 microvolt per volt. Ideal op-amp characteristics are something like this. Okay, it is like this. But practically, due to this, it is like this. So we have positive saturation, negative saturation like this. By the plus V and minus V, we are applying at the supply terminals that acts as the saturation limits for the op-amp. So practically, it is like this. So ideally, it is like this output voltage. Practically, due to the slew rate limitation, it is like this.